Welcome. Today, we're going to be statistical detectives. We're diving deep into a mystery, hunting for a hidden culprit in our data that can fool even the sharpest minds and lead us to some seriously wrong conclusions. So, take a look at this chart of China's GDP. On the surface, it seems to tell a really simple story, right? Strong, consistent growth. It looks like a nice, smooth path you could pretty much predict into the future. But what if I told you that this upward trend could be a complete illusion? That it's hiding a deep, underlying randomness that makes forecasting basically a fool's errand? To crack this case, we first have to understand that we're dealing with a classic case of mistaken identity. This is really a tale of two very, very different kinds of trends. That's exactly it. Think of it like this. One path is like following a carefully drawn map, while the other is like wandering aimlessly through the woods. Yeah, both paths might lead you uphill for a while, but only one is predictable. And telling them apart? Absolutely critical. Okay, so let's meet our two main players here. On one side, you've got the deterministic trend. Think of this as steady, reliable progress. It changes by a pretty much constant, predictable amount every single time. But on the other side, we have the stochastic trend. This one is a total wild card. It changes by a random amount each period. Sure, it might go up on average, but every single step is basically a roll of the dice. And this slide just nails the difference. The deterministic trend, that's the smooth, predictable line, it knows exactly where it's going. The stochastic trend, though, is the jagged, erratic one. It's often called a random walk, which is the perfect name for it because it's essentially just stumbling from one point to the next with no real memory of where it started. Now, you might be looking at this and thinking, okay, so one is a little bumpy. So what? Well, that bumpiness, that underlying randomness, is exactly what makes the stochastic trend the villain of our story. So let's get right to the heart of it. Why is this randomness so treacherous? What makes it a problem that can totally derail our analysis and lead us astray? First off, it has something called unbounded variance. Okay, think of it this way. With a stable, predictable trend, your forecasts might be off by a little, but they usually stay within a reasonable ballpark. With a stochastic trend, that ballpark of uncertainty just gets wider and wider and wider over time. Your forecast pretty quickly becomes less of a prediction and more of a wild guess. You're not just off by a little, you could be off by a catastrophic amount. Second, this kind of randomness just breaks the fundamental rules of statistics. The very tools that analysts rely on to make confident predictions, the ones that tell us how reliable our findings are, they just stop working. It's like trying to use a compass at the North Pole. All your standard instruments go haywire, and you just can't trust your results anymore. And this might be the most dangerous part of all. It creates spurious correlations. Two completely unrelated things that both happen to have a random stochastic trend can look like they are perfectly connected. This is how you end up with bogus conclusions, like saying ice cream sales cause shark attacks just because both tend to go up in the summer. It makes you find relationships that simply aren't there. So what do we call this statistical villain? It has a name. It's called a unit root. A unit root is the technical signature of one of these non-stationary stochastic processes. And here's the crucial takeaway. When a series has a unit root, any shock, like a recession or a pandemic or a major policy change, has a permanent effect. The series never forgets it. It never returns to its old path. It's been knocked onto a totally new, random journey, forever. Okay, this brings us to the next phase of our investigation. Now that we know who our culprit is, we've got to learn how to find it. It's time to go hunting for unit roots in our data. We need a strategy, right? A set of detective tools to figure out if our data is infected. So let's open up the toolkit and start examining the evidence. Our first clue is a visual one. It's kind of like a statistical fingerprint. We use a tool called a correlatogram, or more formally, an autocorrelation function plot. What this does is it shows us how each data point is related to its own past values. It's a picture of the data's memory. And right here, you can see two very different fingerprints. On the left, that's a healthy, stable series. See how those bars, the correlations with the past, they drop to basically zero almost immediately. Its memory is super short. But now look at the chart on the right. For a series with a unit root, those bars decay so slowly. It has this long, persistent memory of past shocks. That right there is our smoking gun. But, just like in any good detective story, visual evidence isn't always enough to get a conviction in court. A series might look like it has a unit root when it actually doesn't. We need something more rigorous. We need to bring our suspect in for a formal interrogation. And that's where formal statistical tests come in. Now, there are a bunch of them, but one of the most famous is the Augmented Dickey-Fuller test, or just the ADF test. These tests are specifically designed to check for the presence of a unit root and give us a clear statistical verdict. Case closed.
So we've identified the problem, and we know how to test for it. Now for the most satisfying part of any mystery, the resolution. And in this case, the fix is, well, it's surprisingly simple and really quite elegant.
Let's go back to our original crime scene. Here's that seemingly smooth GDP data for China, and right next to it, its correlogram, its fingerprint. Look at how slowly those bars decay. That is the classic signature of a non-stationary series that's hiding a unit root. So, how do we fix it? It's a simple two-step process. First, you confirm you've got a unit root with one of those formal tests. And second, you apply a beautifully simple technique called differencing. Instead of looking at the GDP level itself, you just look at the change in GDP from one period to the next. It's a simple subtraction, but it is incredibly powerful. And here it is, the aha moment. On the left, that's the difference GDP data. The strong upward trend, it's gone. It now looks like a stable, stationary series. And the proof is right there on the right. Look at its new correlogram. The bars die out almost instantly. The long random memory has been totally erased. Our data is now clean, well-behaved, and ready for some reliable analysis. So, we've solved the statistical case. But why does this all matter so much in the real world? I mean, this isn't just a technical exercise for stats nerds. It's at the absolute heart of some of the biggest debates in economics. It all comes down to this massive question. Do big economic shocks, like a major recession, cause permanent damage? Or do we always eventually return to our long-term trend? See, if GDP has a unit root, it means a severe recession permanently lowers our economic potential. We never get back to where we would have been. But if GDP is just trend stationary, it means we always bounce back. The answer to that question completely changes how we should respond to an economic crisis. So, the crucial point here is this. What looks like a clear path forward might just be the results of a long series of random steps. And the next time you see a chart with a nice, clean trend heading upwards, I hope you'll just pause for a second and ask the detective's question. Are we looking at a predictable destiny, or are we just watching a random walk?